So good morning, everybody. So my name is Sitou Afanou, and my colleague Cedric Lelionnais will present computer vision and machine listening application for logistic operation. So on my side, I come from SNCF. I'm a computer vision and machine listening engineer, and I worked for 2 years with the automotive field at Afanou before coming at SNCF. And since 2016, I am AI specialist in SNCF.
So I'm Cedric Lelionnais. I've been working at the Stock Engineering Center of SNCF for 3 years. And my job is to design some tools for the qualification of safety equipment in the field of artificial intelligence.
Okay, as an introduction, yesterday we saw a lot of application of AI, and as you can all imagine, there are huge opportunities that AI can provide for several companies. It can help provide new services or developing new systems or increasing performances. So AI is quite a powerful tool for industry. For railway companies, it can help maybe increasing safety or increasing comfort of passengers or increasing their security. That is why in SNCF we are trying to set up a competence cluster in order to develop some applications, some system that we can integrate on our rolling stock in order to provide some value added to our customer. So as you can see, there are a lot of use cases that can be managed by AI. On this slide, we group them in 4 groups: safety, security, operation, and maintenance. For example, from operation use cases, we can implement automated empty vehicle check or people counting in the train. For security use cases, we can implement frontal obstacle detection or incident detection like incivility or gunshot or something like this. For safety use cases, it can be track monitoring or door access monitoring, as we saw it yesterday. And for maintenance, it can be failure detection by audio analysis and hardware detection. But as we only have 20 minutes, we will just focus on use cases in during boxing. So on my side, I will present use cases for operation and security, and Cedric will represent use cases for safety. So the first use case is about automated empty vehicle check. So what is the context for this use case? Sometimes when some trains reach their final destination, their final station, and they are moving back to the maintenance center, sometimes some people remain in. And in this case, the train brings them to the maintenance center. As you can imagine, it can be risky or dangerous for them because in the maintenance center, they can face some dangerous situation like moving trains in the depot, some high voltage equipment. So that is why we are trying to develop an AI system which uses the CCTV cameras integrated in the train to analyze video frames and detect if someone is remaining in the train before the train moves back to the maintenance center. Technically, it is based on a 2-stage convolutional neural network. So a convolutional neural network is a kind of neural network which is specialized for image treatment. So you can have convolutional or you can have recurrent. For this use case, we use a neural network in 2 stages. 1 stage for detection with an algorithm called faster RCNN, and 2nd stage for classifier, as a classifier. So it is what we call a ResNet 50. And the whole architecture was trained on a Microsoft dataset called Coco. So you can see here a short overview of a video we recorded on a train near of Paris. It is a suburban train. And as you can see, the algorithm can detect people in the field of view of the camera. And for each people detected, he can associate a label, so a class name. Here it is V1. And it associates with each class name a confidence score. So, as you can see also, it can also detect occluded people. So, on the right of the video, there are somebody who is occluded by the seat, and the algorithm can even detect him and associate a class name and a confidence score. So it is quite a powerful and interesting tool. Second use case is about frontal obstacle detection. So as you know, sometimes in commercial service of the train can hit some obstacle. So it can be an animal or a person. So in this case, the driver has to make sure of what kind of obstacle he hits. So it can be difficult for him, mostly when weather conditions are difficult, like raining or snowing or fog. Sometimes also, the driver has to leave his cabin to inspect by himself the train to make sure of what kind of obstacle he hits. So it can be shocking for him, mostly if what he hits is a person. So to avoid this kind of situation, we develop an AI system which is based on face-forward camera. So it is a camera mounted on the head of the train. So the AI system can analyze the reference provided by the camera and detect what kind of obstacles are in the field of view of the camera. So technically, it is the same concept as the previous one, so a two-stage convolutional neural network. And this is also a short overview of some tests we performed. And as you can see, I don't know if you can see it clearly, but the system is detecting coals and ships on the track. And for this case also, it associates a class name with a confidence score. The third one is about pose estimation. Pose estimation can be used on trains to detect if some violent situations are in progress. For example, if somebody is holding a knife or a gun or something dangerous, we can use pose estimation to detect if something wrong is in progress. So the aim is to detect something dangerous and send a notification to an operator, which can send a police team if needed. Technically, it is based on a neural network called Google Net. So as you can imagine, it is developed by Google. And in this neural network, you have 23 convolutional layers. And the whole architecture was trained on a dataset called Cambridge Landmarks. So also, a short overview. As you can see, for each people in the field of view of the camera, the system draws some key points on the person, and each key point, after drawing each key point, he draws some segments. So each segment can represent people leg, people hand, or their back. So as you can see, the system can do that, and the goal is to use this segment and this key point, provide this data to a system who can analyze if the pose of the person is dangerous or not. So in this video, I don't know if you can see it clearly, but this one, the people this person in the center of the video is holding a gun. But I don't know if you can see it clearly. And last use case for me is about machine listening and audio event detection. The aim is quite the same as the previous one, but here, instead of using cameras, you can use microphone, you can use sound. Because sometimes cameras can be operated, maybe in some trains, there are no CCTV. So in this case, we can use audio, microphone, okay? Using sound, we can treat the sound and detect if something dangerous is in progress, like a scream or a gunshot or a gas break or a tagging spray. Technically, it is based on what we call a CRNN. So CRNN is the combination of convolutional and recurrent neural network. Okay, so it is a combination of these two kinds of neural network. And to train this network, we use our own dataset. So it is not a public dataset like the previous one. It is our own dataset we developed by our side in SNCF. So what is the process for each sound, for each sample of sound provided by the microphone? The system can transform the sound in spectrogram. So it is what you can see on the right top. And the system can parse each spectrogram to find some fingerprints of what can be an event. So a scream, or something dangerous. So in this case, you can notice the system found on events in the spectrogram. So it is a system which is in progress in SNCF, and we are going to test it very soon.
You have 3 minutes left.
3 minutes.
3 minutes.
Okay, so very short. It's a use case about attract signaling detection. The goal of this function is about the project of driving assistance to strengthen safety on trains. Today, drivers are faced to risky situations, like stop signs, which can be unsurmountable, or a zone within signaling transmission is not covered. So drivers have to be very vigilant to respect the speed. To help the drivers in this sense, we are focusing on the identification of both traffic lights and signs by machine learning. So let's take a look now on this demonstration. It's an extract of a video taken on a TGV. In the middle of this video, you have the search area where traffic lights and signs are identified. On the left side, you have a window where all event, signaling event is contextualized during the trip of the train. And on the right side, you have an examples of contour detection. The first step of this algorithm is to take the shapes of the objects as a first step of the algorithm before to apply a machine learning algorithm. What is important here is to, even if you use a machine learning algorithm, you have to extract the pertinent features in order to be the most pertinent. So here is for traffic lights, and further I have an example of a speed limit zone, but I don't know if I can jump to further, we have a section where the speed is limited, the signs are identified, but as previously, the shape of the sign is recognized, but after that, the information has to be more identified. For this, we have a pseudo-like art algorithm to apply the recognition. Wait, just for it. It's here. From a functional point of view, this function will complete a set of protection functions on behalf to the future assistance equipment. The heart of this equipment is a calculation of deceleration, which will rely on function detection of signal detection function, and localization function and ground communication competition. As a result of this calculation, the most restrictive information will be alerted to the driver, depending on the degree of protection. This is the architecture proposed for this future equipment. A set of sensors and interfaces are structured around a computational platform. As you can see, we have a system of autotachometry to provide the speed of the train, but also a geo-tracking system to provide more precise positioning of the train in certain conditions of detection. You have also a radio communication for maintenance operations and transmission data, a mapping for georeferencing elements in the infrastructure and georeferencing zones, a speed meter to control command the speed of the train, and an assistance driver to contextualize the signaling events and configure the system. And finally, a camera to implement our functional operation. To conclude this presentation, as shown, developing artificial algorithms is very important today. It's a major issue. So, SNCF and its partners are willing to integrate solutions in-house and for when data are critical and sensitive. The second point is the necessity to get an open hardware platform and an open architecture to implement the algorithms in order to certify, without the necessity to certify them again. And finally, the last point is very important today to be involved in qualification works of certification works of to guarantee the performance and the fitness of artificial intelligence algorithms. Thank you.